Field goal kicker Ray Finkle makes 80% of his kicks. One year in the Super Bowl, he missed all 4 of his kicks. Determine the probability of this happening. Now, there are a couple of ways that you could approach this problem. We're going to approach it as a modeling problem. We're going to model this situation using the binomial random variable. Okay, x is going to equal, pull up my pens here. All right, let's go with green. The random variable x equals the number of kicks either made or missed. All right, so one, as he lines up to kick the ball one time, that's going to be a Bernoulli trial. All right, constant probability of success, and then from trial to trial, we're having no bearing. From kick 1 to kick 2, the probability that the kick goes, let's say, goes in the bucket, it's the same, 80%. All right. So the number of kicks out of 4, we just have to decide here: do we want to talk about making or missing them? All right. In the question, it says, in the setup here, it says missed. So we're going to use complements, and we're going to talk about the success probability from a binomial perspective of missing. Right? It's not that missing these kicks is a good thing for Ray. In fact, it's bad, but here we want to model missing them. All right? So I'm going to set it up that way. So x is the number of kicks missed by Ray. We'll just say Ray out of 4. That's our random variable. And it can take on, he could miss 0 kicks out of 4. That means he made them all. He could make 1 kick out of 4. So he could like make the first one and miss the next 3. Or he could like miss one and then make one and miss. Miss half of them. Miss 3 of them, or miss 4 of them. And in the Super Bowl, he did miss all 4. So I'm gonna use the formula to figure this out. Okay. So watch this. We're gonna set this up as, let's set our parameters up. We have n equals 4, and then we have, using complements, if there's an 80% chance a kick will go in the bucket, then there's a 20% chance it won't go in the bucket. All right? Now, we shall use the multiplication rule combined with combinatorics and Pascal's delights, and you end up with the incredible binomial random variable distribution mass function. And probability distributions can come as a function, as a graph, or as a table, right? We have a binomial table. You could certainly use that to solve this situation. So what was the probability of this happening? We have n choose x. We want x combinations out of n kicks, right? In this case, 4 tries, n trials, times the probability of success raised to the x power, times, you can either use q, pq, or 1 minus p. I'll just use 1 minus p because that's what I want to do. Raised to the n minus x power. Notice that p plus 1 minus p gives you 1, and then x plus n minus x gives you n. Little trick there to make sure you have everything right. So this thing right here, we want to find out the probability that the random variable takes on the value of 4. So we want 4, choose 4. How many ways can that happen? How many combinations can we get there? That's an interesting one. Then probability of success, 20%, raised to the 4th power times 1 minus 0.8. See what I did there? That was on purpose. Raised to the 0 power. And look what happens! We just get the multiplicative rule for independent events. 1, and you get 0.2 to the 4th power. I cannot claim to know what that is, so what I'll do is go to the internet and type in binomial applet and go here, put 4 in there, put 0.2 in there, and then put in here. Oh man, once you have this picture, it doesn't even matter. But there's not a lot of probability out there, right? I mean, what happened to Ray Finkle? It's like a 1 in 1,000, 1 in 1,000. All models are wrong. Some are useful, right? You might argue, hey, kicks are not independent in that voice. And I'd say, okay, well, all models are wrong. Some are useful. That's what George Box used to say. You'd say, who's George Box? And I'd say, think about the box plot. And that's George Box. Great quip. All models are wrong. Some are useful. That's really talking about how we're trying to make sense of the world. Okay? There's a lot of assumptions we place on to model with the binomial distribution. Right? We need independence. Right? We need constant probability of success. But a lot of sporting events or outcomes are treated in a very stochastic way. Stochastic being, I think, just a synonym they use in other countries for independent events. All right. And there's a class at UCF called Stochastic Processes. I highly recommend that. That's a really good course. Monopoly being the stochastiest of them all. The probability here is just like really small. Now, let's consider the following. What if in this problem, notice how I said that I set up the random variable so that it was like x equals 4, and I thought a bit and said, okay, we don't want 80%, we want 20%. What if instead we stuck with the 80%? We're going to get the same answer as long as we change what? Well, man, this is really giving it away, isn't it? Please be the same, please be the same, please be the same, please be the same. Yes. Hey, what are you? Shouldn't be there. Secret. Whoa.